Hi everyone. In this video we're going to study a reaction where we add alcohols with acid to an alkene. This reaction is essentially the same as the hydration reaction where we add water to an alkene, so I have it drawn here for comparison. In the reaction involving an alcohol, we will add H and an OR group to our alkene. R is the generic letter that organic chemists use to represent any alkyl chain. Here I've used methyl as my alkyl group, but it could be an ethyl, propyl, isopropyl, whatever you want it to be depending on what you want to have in your product. And this generates an ether functionality. We have that ROR arrangement of our carbon and oxygen atoms. In the hydration reaction, for comparison, we have a situation where we add an H and an OH to our alkene to generate an alcohol. The only difference here is due to the structure of our reagents. We have an HOH that we're adding to our alkene versus here we're adding an HOCH3. So the two components that are added are different solely due to the structure of our reagents. Let's look at a few examples to better understand the regio and stereochemical outcomes of the addition of alcohols to alkenes. In the first example here, we have a terminal alkene that is disubstituted at 1 carbon. So we have our choice between producing a tertiary ether linkage. Note the R group here is my isopropyl group, or I have the choice to produce a primary ether linkage here. Experimentally, we observe that this is our major product, and this is not observed at all. Again, we see that the regioselectivity is consistent with Markovnikov's rule, where the hydrogen has added to the less substituted carbon. Before we do our second example, I would like you to predict how many constitutional isomers could be produced in this reaction. We would answer that question by adding our group, our OR group, to each carbon of the alkene, and then determining if these products are the same or different. Because these carbons both have an ethoxy group on the second carbon, these are in fact identical compounds. So there is one possible constitutional isomer to produce in this reaction. There is no difference in the substitution of these two carbons of the alkene that would lead to any regioselectivity. In terms of stereochemistry, both of these reactions have produced one chiral center, and it's experimentally observed that those configurations are mixed at that center. So both of these reactions produce a racemic mixture, an equal composition of 2 enantiomers. In a later video, we will better understand the regioselectivity and the stereochemical outcome of this reaction. Thanks for watching.